Let me get it so I can write on the PowerPoint if I need to. The factors that affect the reaction rate we've already talked about: temperature, frequency of collisions, orientations of molecules. What does that mean?
The way they're arranged.
The way they're arranged, and that matters. And then the energy needed for the reaction to take place, which is activation energy. Have you talked about activation energy in biology? You don't remember?
I remember.
Maybe? Vaguely? No, didn't talk about anything in biology? All right. Oh, that I told them wrong last block, so maybe they'll watch the video because I couldn't remember this rule of thumb. That the rate constant doubles with approximately every 10 degrees rise. I told him when it doubled. I couldn't remember the 10 degrees. I couldn't remember it. So hopefully they'll watch the video. There's our little demo the other day, right? All right, so the rate constant is temperature dependent. So K is dependent on temperature, and it will change as temperature changes. And so as a general rule, the rate constant K will double with every 10 degrees. Probably because I didn't start at those slides for last block. But anyway, we'll talk about that and how that relates to activation energy in a minute. All right, collision theory. This is the conceptual piece. This is the theory for how or why some reactions or some collisions produce a reaction and some do not. So first of all, it says that they have to collide. And then if they do collide, they have to collide with the right amount of energy and the right orientation. So let's look at the orientation. Look down here on, let's see, right here. All right, so before the collision, these two things are lined up so that the two green ones, which are chlorine, hit. When they collide, the two chlorines join together and they produce an effective reaction, right? It turned into something different. In this case, this molecule's oriented differently. So when the green chlorine hits that molecule, it doesn't hit the green chlorine, and it just bounces back off. It doesn't produce an effective collision. So orientation matters, or that's the theory. Bonds have to be broken in the reactants and then formed in the products, but in order for them to form, they've got to be close enough together, right, to be able to form them. All right, so aligning the molecules properly can lead to chemical reactions. So not every collision is effective. Some are. They have to have the right orientation. The other thing they have to have is the right activation energy. They have to have a certain amount of energy. So the activation energy is the minimum energy needed for the reaction to take place. It is easier to see on this little chart. Let's look at this little diagram. This is the energy. This is the reaction progress. So right here are the reactants. Let's see if it'll let me write. Right here are the reactants. Right here's the energy of the products. All right, and then up here is something called an activated complex. The activated complex is some like middle ground. It's right after these bonds have broken, the reactant bonds have broken, and right before the product bonds form. So it's this kind of limbo stage where all these atoms and molecules are sitting there with bonds broken and bonds just about to form. And that's the activated complex. It takes energy to get to that point, right? Because you have to break those bonds. So it takes energy to get to that point. So the collisions that happen have to collide with enough energy to basically get over this point. Okay, and if they can get over it, then they can produce a product. All right, this particular reaction, the activation energy goes from right here, where the energy, right, think about this as a graph as numbers going up the side here, right? Think of this as an XY graph, and there's numbers going up. So this is the energy of the reactants, and then up here is the energy of the activated complex. That difference is EA. What's EA? Activation energy. So that's the activation energy. Then the difference between the energy of the reactants and products, they have it labeled as delta E. What will we label it as? Delta H, right? Because that is our, right, we know work, it is delta H. So that's delta H of the reaction. Is this reaction that's drawn endothermic or exothermic?
Exothermic.
Think energy of the products minus energy of the reactants. Is it going to come out positive or negative? Well, put numbers. If this is a 1 and let's say this is 10, it's going to come out negative because 1 minus 10 is negative 9, right? So delta H in this case is negative, so that makes it exothermic, which most of your brochures looked really good, by the way. If you didn't do them because you were out, you need to get those in. They will go in 4th 9 weeks grade, but anyway, you need to get them in if you were out. All right, so that's exothermic. What would an endothermic graph look like? I need a. Will it let me write on? It would be higher on the right. Right. Let's see if it'll let me. See, why in the world does this not let me have a pen when I go to a blank screen? I don't understand. All right, so I'll just draw it down here. All right, so endothermic's is gonna look more like that, right? Where here's my reactants and here's my products. Oops. So my activation energy for this is from there to there. Where's my delta H? Products minus reactants. So that amount is delta H, right? So this one's endothermic. And these are in your notes as well. They're on page, or handout 5. They're at the bottom of that page with the half-life on them. They are there. All right, so what happens if I reverse the reaction? Let's say I take this top reaction and I run it backwards. Whoops. Yeah, it becomes endothermic. So if I run it this way, right, then these become my reactants and these become my products. It does become endothermic. What's the activation energy for the reverse reaction? Right, the delta H plus the E of the activation of the forward. So it's this whole distance, right, from the products to there. So that whole distance would be the activation energy of the reverse reaction. All right, what do catalysts do? They speed it up. How do they speed it up? Lowering the activation energy. They do. I was trying to make it a race. All right. So catalyst will somehow change the mechanism so that this little hump basically gets lower. It changes or lowers the activation energy. So now it only has to have this much energy, right, instead of the whole thing. All right, it could look like, and can you see if I draw up here? What, like, let's say this was the original reaction. What if it looked like this? What is that? Two catalysts. It's not two catalysts. It's a two-step mechanism. Okay, right? Here's the first step, and the first step has an activation energy to there, and the second step has that much activation energy. You see it? So a catalyst could have been applied, or we could have changed the mechanism, or the catalyst could have changed the mechanism and made it a two-step process that changed, but either way, it results in a lower activation energy, right? So more molecules, more collisions are going to be effective because more of them will have enough energy to get over that bump. Which step in what I drew, I don't know if you can see it well enough, but which step, step 1 or step 2, which one would be the fastest? Step 2. Why would step 2 be faster? Less activation energy, right? So it's going to be faster. So in the one that I drew, the slow step is probably the first step, right? Because the activation energy is higher. Okay, so do we get, these are called reaction coordinate plots. Sometimes reaction progress. Most of the time, I want to say the AP test is reaction coordinate graphs or plots. You do need to know them. You need to know them well. You need to be able to label them. You need to be able to pull energies off of them. You need to be able to tell me if they're endothermic, exothermic. You need to be able to draw in what a catalyst does to the activation energy. What would an inhibitor do? Yeah, somehow it's got to make the activation energy higher because it's got to slow the reaction down. So to do that, it's got to make this activation hill higher somehow. Okay? All right, we get those? We think we get those? hopefully. All right, so look at I probably already answered this one for you. Rank the following, those three graphs from slowest to fastest.
That's the other way.
Slowest to fastest.
2, 3, 1.
Right, 2, 3, 1, right? Slowest to fastest. So slowest is going to be 2. It's going to have the biggest activation energy. Does it make any difference that one's endothermic and the other two are exothermic? No, it makes no difference. How fast has to do with that activation energy. So yeah, so 2, 3, 1. All right, so the two things that are important for you that produce effective collisions. They have to have the right orientation, and what else? And enough energy. And they have to collide with enough energy. Or more energy than the activation energy. With enough energy to get, I don't know, over the activation energy. I don't want to say hill. What do I say? I didn't phrase that very well. Maybe the activated complex. Energy, the bump. All right, so you know what I mean. They have to have enough energy to get over this, to overcome the activation energy, I guess. All right, so those are the two important things. All right, then how does temperature affect rate constant? Huh? All right, when we say temperature of the gas particles, we say that temperature is related to the kinetic energy. Does every gas particle have the same identical kinetic energy? If they're all at 273, do they all have the same kinetic energy? No. What do they have though? We say they all have the same, but do we mean each individual molecule? No, we say they have an average kinetic energy, right? So one molecule might be running faster than another one. But an average, temperature is an average of the kinetic energy. So the higher the temperature, the more molecules or the more atoms or molecules you're going to get that have enough energy to get over the activation energy, right? This may be the average temperature, but see how it spreads out the distribution? So more of them, anyway, it doesn't matter. Is at a higher temperature, more of them have enough energy to get over the activation energy. So that's why temperature affects rate. All right, it also affects rate constant. All right, what we decided to do was not to, kill you with the math, right? That's the Arrhenius equation. This is the relationship between activation energy and rate constant and temperature. So that's how they're all related. The problem, the math gets a little tricky. So we won't put the math on the test, but conceptually you've got to remember it. So this is your rate constant, just like in R equals K, right? That's K, that's rate constant. A is a constant, it's the Arrhenius constant. What's E? Yeah, that E from the natural log, right? It's your math E. So 2.3 whatever it is. And then what's EA? Activation energy. What's R? That universal gas constant. And then what's T? Temperature. And temperature has to be in Kelvin. 0.08206 because it's in liters. No, this is activation energy. Has to be the joules. Has to be the 8.314. Yeah, it has to be the 8.314 because we need joules to come out for energy, right? All right, so it'll be that one. Temperature has to be in Kelvin. And then Arrhenius is just, the Arrhenius constant is just a number, and then K. All right, if we linearize that, that ends up being a curve. So if we linearize that by taking the logarithm, the natural log of both sides, we end up with this. That's what's plotted in this graph. This is y equals mx plus b. Let me rewrite it like this and you might see it better. Negative EA over R. All right, now look at what's plotted and look at that equation. Now do you see it? Look, right, here's y, right? That's what's plotted on our y-axis. Here's our x. So the slope of that line, right? That's where this comes from. The negative activation energy over R. And then what's ln of A? Right, which is what? That y-intercept, right, right. So,
B is gonna be the same for everything.
is it a constant forever? Or is it a constant for each particular reaction? I don't remember off the top of my head. I think it's specific to every reaction. Most of the time you don't need it because most of the time you don't use it in these two forms. Usually you would use it in this form, and what they've done is they've taken a ratio of one over the other and the A's drop out. And then that way you could find, if you knew the activation energy and you knew the rate constant at one particular temperature, you could find the rate constant at another temperature. It is supposed to just be, this isn't supposed to be there. It's supposed to just be the concentration of that over time. All right, so we won't do the math, but conceptually you need to see what happens to the rate law. All right, so look at this. If temperature, this is 1 over the temperature, right? So if I increase the temperature, which way am I going on that x-axis, right or left? Left, right? Because if I'm increasing the bottom of that fraction, it's getting smaller and smaller and smaller. So as I'm increasing temperature, oh, wrong thing, PowerPoint. As I'm increasing temperature, I'm actually going this way. What's happening to K? It's getting less and less negative, right? So it's increasing. So is the natural log of K is increasing. So is K increasing or not? If I'm going from a negative to a positive, think about that. If you go from a negative natural log to a positive natural log, what happened in your number? Where do you cross from negative to positive? At 1, right? So if you're below 1, you're in the negatives. So this is getting bigger and bigger and bigger. When it got to 0, it would be at 1. And so it is getting bigger. So an increase in temperature equals an increase in rate constant. That part you need to know. And what was the general rule we just saw at the beginning that I forgot to tell 7th block? Every 10-degree increase in temperature usually doubles the rate constant. All right, so the example I was going to have for you next was to plot it. There was data to plot and let you figure out this graph and do all this. We will leave that off. We'll just leave the concept conceptually for your test. We won't put the math. Okay? And that way at least you still get a relationship between temperature and rate constant, but we don't have to fight this math all night to practice. Okay? All right, that's it. That's the end of the new stuff. Is it? Well, and that's what I have for you is to review the old stuff as well. I have a review sheet for you. And I have answers to that I'll put on Canvas. I will put the PowerPoint on Canvas as well. I got to put the PowerPoint on Canvas. I need to put your review sheet and the answers to the review sheet on Canvas. And then 7th block asked for an extra mastering chem or extra initial rate and integrated rate law practice. I don't know if mastering chem will be the best option for that. It might be that I put extra practice on Canvas. But I'll stick you an announcement on Canvas, and that's what I'll